Hi everyone, I hope that you're all doing well. So this is going to be the first of my series of video lectures covering all of the content from chapter 6, which is what we're meant to be doing this week. Right, so what I'm going to be covering in this video lecture is section 6.4, and 6.4 deals with actually using matrices to actually solve systems of equations. Now, before we continue, what I want to do is actually quickly recap on where we had ended last. So this is the last example that we had covered when we last met. So given a system of equations, the question is, how do you take the system of equations and rewrite it in matrix form? Right, so I'm going to call this system of equations star. This is what it's now being labeled. Remember, when we had unpacked the information, we had seen that we could create a matrix labeled A, where your matrix A was called a coefficient matrix because observe what has happened. We have taken the coefficients of the variables x1 and written it in column 1, taken the coefficients of the variables x2 and written it in column 2. So that is basically what we have done. Thereafter, we had created a matrix X, where X is called a variable matrix, which lists the variables that was used in this system of equations star. So that was variables X1 and X2. And finally, we wrote down a matrix which we labeled B, where B consists of all of the constants from your system, meaning it's all of the constants on the right-hand side of the equality. So that's 4 and 7. Once you have now separated everything, into each of these components, these matrix components, we then observe that the original system star can now be expressed in the following way. It can be expressed as A being multiplied to X, matrix A being multiplied to matrix X with an equality, and that is then equal to the matrix B. So that's what's actually happening. And your original system of equations expressed in that way is now equivalent to expressing it in this way in terms of matrices. So that was an important bit that I just wanted to recap on before we move on. Now we're starting with the new work. So it's all about using matrices to solve systems of equations. So in order to talk about that, we first need to have an idea of what type of operations are we allowed to use when solving these systems. So these operations are called elementary row operations, and actually you have already been exposed to elementary row operations because you had used them in the method of elimination. So this was done before. So remember, if I gave you a system of two equations and we were solving using the method of elimination, then maybe we would have chosen to eliminate variable y. How would we have done that? Firstly, we would have multiplied one of the equations by a constant number and thereafter added the two equations together to eliminate one of the variables. So that is what we would have done in the method of elimination. So I am going to spend the next few minutes talking to you about what these elementary row operations will be for matrices, but remember, it is actually operations that you worked with before. So before we talk about them, let's talk about how do we take our system of equations and express them into matrices. So given a system of equations, the first thing that you should do is align the variables. So example, let's say we started off with this system of equations. So we've got two equations in two variables. So we've got variables x and y. Right, so we can then label the equations and align the variables as follows. So here, originally, we have variable x followed by variable y, but in the second equation, we have firstly variable y, then followed by x. So this is what I'm referring to when I say alignment. So you rewrite the equations to express all of the variables x first, followed by all of the variables y, as done on the part that I am pointing to, and thereafter label each of your equations. But this is something that you are already used to, right? So as you can see that this new rewritten system does indeed satisfy those conditions. Now, we have a system that's been labeled and variables have been aligned. So how do I now rewrite it in matrix form? The matrix form that we require is called augmented matrix form, right? So how do I write it in this form? The first thing you do is write down your coefficient matrix. And remember, I just recapped on what the coefficient matrix of the system is. Thereafter, you will place a vertical line to denote the equality, because here are the equal signs in there. And you will follow that by the constants matrix. Remember, the constants dealt with the constants on the right of the equality sign. So what does this look like? So here we have a coefficient matrix written down. Right, so that is certainly the coefficient matrix of that system, because you've got 2 and 1 as coefficients for x, and that's been written down there. You've got 7 and -1 as coefficients for y, and here you have it written down there. Followed by a vertical line. Right, so here is our vertical line for equality as in number 2. And thereafter, on the right-hand side, we write down the constants matrix. So that's what's been done here. So this matrix here, expressed as follows, is called an augmented matrix. So this is the procedure you will now follow. Given a system, realign the variables, you will have to label your equations and write it in augmented matrix form. Right. So here we have this written in augmented matrix form. So once again, let's label the equations. So we see that in row 1, this represents the first equation, so we will label that R1. In row 2, we then have our second equation, and we will label that R2. So we have an augmented matrix, we have the 2 rows being labeled. So the question now is, what are the row operations? So the row operations, as mentioned earlier, are exactly the operations that you had encountered before. The first row operation tells you that you are allowed to change 2 rows of a matrix. So in the above example, you can interchange row 1 and row 2, meaning you can, in place of row 1, write down row 2, and in place of row 2, write down row 1. So this notation here is describing exactly what was just said in words. Elementary row operations number 2 says the following, that you are allowed to multiply a row, meaning any row in the matrix, by a non-zero number. So by any constant number, ensuring that it's not 0. So this is expressed as follows in the notation that's being highlighted. So for example, you can rewrite in place of row 1, 2 times row 1. So that is an example. And the final elementary row operation that you are allowed to use is to add a multiple of one row in a matrix to another row in that matrix. So for example, we could then add a multiple of row 1 to row 2. So for example, I could take 2 times row 1 and add it to row 2, and that will be replacing the entries in row 2. So these are the only 3 elementary row operations. They may seem cumbersome at first, but you will get used to using them within augmented matrices. Right. So what is the aim of this section? Remember that the aim is to use matrices to solve systems of equations. So what have I given you so far? The tool so far that we have encountered is how to write down an augmented matrix, and then given your augmented matrix, what are the row operations that you're allowed to apply to it? There's one more piece of jargon that we now need to introduce, and that is the definition of a reduced matrix. So a matrix is called reduced provided the following are satisfied. The first rule is that all rows of zeros are in the bottom of the matrix. So consider matrix X and consider matrix Y. Notice that in each of these examples, the rows containing zeros are indeed at the bottom of each matrix. So both X and Y satisfy number 1. The second property that a reduced matrix satisfies is as follows, that for every non-zero row, the leading entry must be the number 1. What do I mean by a leading entry? The leading entry in any matrix is the first, what do I mean by leading entry in a row? A leading entry in any row is the first non-zero entry in that row. So consider matrix X and look at row 1. In row 1, the first non-zero entry is indeed 1. So that is a leading entry and it is indeed 1. Right. So property 2 says that the leading entry must always be 1 that has been satisfied in X, and all other entries in the column must be 0. So continue looking at X. We have a leading 1. Are all other entries in that column 0? Yes, it is indeed 0. If you look at column 2, you will also notice that you have another leading 1 in here with zeros above it and zeros below it. Right, so in the above example, we notice that both X and Y satisfy condition 2. So let's look closely at matrix X. Why does it satisfy condition 2? In row 1, the first non-zero entry is 1, and we notice that all entries above and below this 1 in column 2 is indeed 0. In row 2, the first non-zero entry is also 1, and all entries above 1 and below 1 are once again 0. So matrix Y satisfies condition 2. Right, and then condition 3 says the following. The leading entry in each row is to the right of the leading entry in any row above it. Right, so let's look at matrix X. So here is your leading entry. It was the number 1, and that was occurring in row 1. Now let's look at row 2. The leading entry was once again in the number 1. And notice that in row 2, the leading entry is on the right-hand side of the leading entry from the row above it. So that has been satisfied. But consider matrix X. You have a leading 1 here and you have another leading 1 in here, right? But notice that in row 2, the leading 1 is on the left-hand side of the leading 1 in the row above it. So therefore, matrix Y does not satisfy condition 3. Right, so that's what's being stated here. So any matrix that satisfies all 3 conditions that were just stated is called a reduced matrix. And this concept is very important. Right, so in addition, before we move on, whenever you have leading entries and those leading entries are in fact number 1, then we call those leading entries leading 1s. So you might find me interchangeably saying a leading entry or a leading 1, but it's going to mean the same thing, right? So just take note of that concept there, or that definition. Right, so let's look at examples. So we have 6 examples here, and the question is, which of these matrices are reduced? So basically explain if they are reduced or whether they're not. Right, so if it's not a reduced matrix, it then means that it does not satisfy one of the 3 conditions that we just mentioned. Right, so let's look at matrix A. Right, so firstly, the first condition said that rows of zeros must be at the bottom. So there are no rows of zeros, so therefore that rule is not going to be applied here. So it's vacuously true for part A. So now let's consider the second rule. The second condition said that the leading entry must be 1, the first non-zero entry must be 1, and it must have zeros above and below it, right? So in row 1, we see that the leading entry is 1, and it has zeros below it, so that's been satisfied. But look at row 2, the leading entry is not 1, it's 3. So that means condition 2 has not been satisfied. So therefore, matrix A is not a reduced matrix. Let's look at matrix B. So has all the conditions been satisfied? There are no rows of zeros, so that's fine. Is the first non-zero entry in each row 1? Yes, that is true. And are the leading entries in each row to the right of the leading entries above it? Yes, it is also true because this one is on the right-hand side of the one that was above it. So that means matrix B is a reduced matrix. Now let's look at matrix C. So again, no rows of zeros. So that's fine. Let's look at condition 2. Condition 2 said that leading entries must be 1. So here is a leading entry, it is 1. Here is a leading entry, it's also 1. But we observe that condition 3 is not being satisfied because notice that the leading entry in row 2 is not on the right-hand side of the leading entry in row 1. So therefore, matrix C is not a reduced matrix. Matrix D is a reduced matrix because there are only rows of zeros and they are written at the bottom, and there's nothing else to be said about leading entries because it's just zeros. At matrix E. So matrix E, observe immediately that there is a row of zeros that is not at the bottom. So therefore that is not a reduced matrix. Now look at matrix F. Is this reduced or not? We have a row of zeros. It is at the bottom. We have that the first non-zero entry is 1 in that row. The first non-zero entry is also 1 in that row. So condition 2 is satisfied. And then we have to check, are the leading ones in each row on the right-hand side of the leading ones to the rows above it? And this is indeed true. This is on the right-hand side of the one above it. So this matrix, which is part of example F, is indeed a reduced matrix. Now the question is, how do you solve a system of equations? We're going to use the method of reduction. Right, so this first step that you need to follow is to take your system of equations, align your variables as I had mentioned before, and write your system in augmented matrix form by labeling each row as well. The next step is to actually just apply the row operations that I mentioned. There were 3 row operations, so you apply them to your augmented matrix, and you will continue to apply them until you obtain a matrix in row reduced form. Now remember, we had just gone through an example of identifying when a matrix is in row reduced form. And step 3, once you have obtained your matrix in row reduced form, you can then stop your procedure and read off the solution to each of your variables. So this is the protocol that we will follow to take a system of equations and solve it using tools and matrices. Right, so there's a very nice and easy way for you to think about this. And I tend to teach it as follows, that you need to think of this as you're playing a game basically. So the starting point is your original augmented matrix. The rules of the game are the row operations that you are allowed to apply to the augmented matrix. And the end point is obtaining a matrix in reduced form, row reduced form. And once you've got your matrix in row reduced form, you can think of it as winning the game. Right, so that's basically what we are doing. Right, so that's the procedure you're following. But now what about the intimate steps that need to be applied? Meaning, how do you apply the row operations to get out a row reduced matrix? That's the question. Right, so this is the strategy you will follow once you've written down your augmented matrix form. Right, so you will work with your matrix from left to right. You will start with column 1, then move on to column 2, column 3, and so on. So it depends on the size of your augmented matrix. So let's say we've just started and we are now in column 1. So when you are in column 1, you will first work with the entry in row 1, column 1. And I'm going to call this entry your pivot entry. So you work with your pivot entry in column 1. You will then convert your pivot entry into the number 1. And you will then convert every other entry in that column to 0. So the question is, how do I convert my pivot entry into the number 1? Remember, you are only allowed to use row operations. So the 2 row operations that could apply here is that you could either multiply that row by a non-zero constant, or you could swap any 2 rows such that you get a number that is 1 in place of your pivot entry. And then how do you convert every other entry in that column to 0? Then the procedure there is to add multiples of the row containing the pivot entry to the row that you're working with. You then repeat this procedure once you're done in column 1. You then move on to column 2 and you work with a new pivot entry. But remember now that the pivot entry is going to be in row 2, column 2. Right? And again, repeat that procedure in terms of converting the entry in row 2, column 2 to 1 and everything else in the column 2, 0. Right, once you're done with column 2, go on to column 3. Once you're done with column 3, go on to column 4. But remember, in column 3, the pivot entry will be in row 3, column 3. In column 4, the pivot entry will be in row 4, column 4, and so forth. So I hope you understand what is happening in each of the steps. Right, so in general, if you're working in the nth column, then you work with the row n, column n as being your pivot entries. So the entry in row n, column n becomes your pivot entry. And the procedure is the same. Make the pivot entry 1 and make every other entry in the column 0. Right, so here is an example which is enforcing this procedure. You are given a system of equations. So this original system consists of 3 equations in 2 variables. We have variables x and variables y. Notice that they have been written such that the variables have been aligned. So this is necessary so that you can write down the correct augmented matrix. So because we have that the variables are now aligned, we then see that the coefficients of x are 2, 2, and 1, so that's been written down. The coefficients of y are 3, 1, and 1, so that's been written down there. We have a vertical line for equality, and then we have the constants on the right-hand side, which is -1, 5, and 1. So what we have is we've taken the original system and we have rewritten it in augmented matrix form. So that's step 1 of our process. Step 2 is to now use the row operations and apply it to your augmented matrix such that we get out a matrix in row reduced form. That's the procedure. Right, so remember I had now given you further tips on how to do that. We're now going to work with column 1. And in column 1, we are going to take the entry in row 1, column 1. So that means we are now working with the entry 1 because that's in row 1, column 1. What do I want to do? Right, so I think I jumped the gun there. So here is the original matrix that we are working with. Right, so we're going to take the entry in row 1, column 1, and that entry is 2. What do I need to do with that? I need to now convert that 2 into 1, and I need to ensure that I get zeros below it. So that's the procedure. So now the question is, how do I convert this 2 into 1? Remember, I had given you an option of 2 row operations. The first one was that you could either multiply this row by a non-zero constant, or you could swap any 2 rows such that in place of 2 you can get 1. So it turns out that in row 3 we do have a 1 right there in that entry. So it means it's plausible for us to swap row 1 and row 3 such that in place of 2 I can now get 1. And that's the procedure that we're following here. It says swap row 1 with row 3. So remember, we now affect row 1. We will also affect row 3, but row 2 remains unchanged. So remember, row 2 is 2, 1, 5, and there it is, 2, 1, 5 unchanged. In place of row 1, we now write down row 3. What is the entries in row 3? 1, 1, 1. And here it is now written down in row 1 as 1, 1, 1. And then in place of row 3, we now write down row 1. So what were the entries in row 1? It was 2, 3, minus 1, and here it is written down in row 3 as 2, 3, minus 1. So that was the procedure. So what we've essentially done is we have converted the entry in row 1, column 1 from 2 to 1, and that is what we wanted. The next procedure is to convert all of the entries below it into zeros. So that's what I'm working to do. So what we're going to do is we are going to focus on this entry here, which has a number 2, and we want to convert it to 0, as you can see there. So the question is, how do I convert the 2 into 0? The question is, what row operation am I allowed to apply to convert the 2 to 0? Right, so remember I mentioned that you can then take a constant multiple of the row containing the pivot entry, and you can then add it to the row that you're working with. So the question is, what multiple of the row containing this entry 1 should be added to this row containing 2 such that I get 0? How do I convert 2 to 0? So what number should be added to 2 to give me 0? That's the question. So this is 2. It means I should add minus 2 to it to get 0. So that means the multiple of 1 that I should take is minus 2. So we take minus 2 times row 1 and we add it to row 2. And that's precisely what's been written down in here. Right, so repeating that procedure, you follow this row operation. And essentially what you do is, we are now going to affect row 2 and leave row 1 and row 3 unchanged. So I take row 1, I write it down as it is. I take row 3, I write it down as it is. And now I apply this row operation to row 2. What does it say? Take minus 2 times row 1 and add it to row 2. So minus 2 times 1, add it to 2, and I get 0. Then take minus 2 times 1, add it to 1, and I get minus 1. then take minus 2 times 1, add it to 5, and I get positive 3. So this is how you obtain the new set of entries in row 2. So we've now converted 2 into 0. I now need to repeat the procedure and convert this 2 into 0, again using a pivot entry. Right, so the same procedure applies. The question that I asked myself is what multiple of the row containing this pivot entry must be added to row 3 such that 2 is converted to 0. So I notice since this is positive 2, I need minus 2 to be added to it to get 0. So that means I'm going to take a multiple of minus 2 times 1 and add it here back to 2 such that that is converted to 0. So that is the row operation that's going to be applied. We need minus 2 times row 1 being added to row 3, and that goes in place of row 3. Right? This means that row 1 and row 2 will remain unchanged. So what are the entries in row 1? It was 1, 1, 1, and here it has been rewritten, 1, 1, 1. What are the entries in row 2? It is 0, minus 1, 3, and here it has been rewritten as 0, minus 1, and 3. But row 3 will now change, and how will it change? It will change according to this row operation. I need minus 2 times row 1 plus row 3. So minus 2 times 1 plus 2 gives me 0. Minus 2 times 1 plus 3 gives me 1. Minus 2 times 1 plus minus 1 gives me minus 3. And that's the new entries in row 3. And observe what has happened. We have indeed created a 1 in place of the pivot entries and zeros elsewhere. So we're done in column 1 and we can now move on to column 2. So in column 2, where is my pivot entry? The pivot entry must be in row 2, column 2. So meaning the pivot entry should be this minus 1, which means I now need to convert minus 1 into positive 1. So how do I do that? Remember, I have two options. I can either swap two rows or I can multiply this row by a constant, a non-zero constant. But we observe that swapping two rows might affect column 1. So that is why we would not go ahead with the idea of swapping. It's safer to multiply this row by a non-zero constant. And I observe that if I multiply minus 1 by minus 1, I get 1, which is what I wanted. So we will multiply row 2 by minus 1. So that means row 1 is unchanged. As you can see, row 3 is also unchanged. And just row 2 will be affected by multiplying each entry by minus 1. So 0 times minus 1 is 0. Minus 1 times minus 1 is 1. And 3 times minus 1 is minus 3. And that is what we get here. So the next step is now to convert the entries above the pivot entry and below the pivot entry into 0. So let's work with the entries above it first. So I need to convert this 1 into 0. And the procedure is to always take a multiple of the row containing the pivot and add it back to that row. So what multiple do I need? If this is 1, what do I need to add to it to bring it to 0? It means I need to add minus 1. So the multiple I'm going to take is minus 1. So I'm going to take minus 1 times the row containing the pivot, which is row 2. So it's minus 1 times row 2, and I'm going to add it back to row 1. So remember, the only row being affected here is row 1, which means that row 2 and row 3 will remain the same. All right, and let's complete this row operation. So if row 2 and 3 are rewritten as exactly as they were previously, let's now write down the entries for row 1. So we now take minus 1 times each entry in row 2 and we add it back to row 1. So minus 1 times 0 is 0, added to 1, I get 1. Minus 1 times 1 is, and then added to 1, I get 0. Minus 3 times minus 1 and then added to 1 and I get 4. So that's the entries there. So I've now converted this entry of 1 into an entry of 0. I now need to repeat the procedure and convert this entry of 1 into an entry which is 0. So same procedure. I need to now work with the pivot entry. Right, so here's my pivot entry, and you always take a multiple of the row containing the pivot entry and add it to the row that you're working in. So if this is 1, that means I need minus 1 to be added to it to give me 0. So that means I need minus 1 times a row containing the pivot. So it's minus 1 times row 2, and then I'm adding it to row 3, which is the row that I'm working in. So remember, row 1 and row 2 remain unchanged. You can see they are rewritten as they were previously. And now I just need to write down the entries in row 3. Remember, the row operation we've written down is minus row 2 being added to row 3. So minus 1 times 0 is 0. Being added to 0 gives me 0. Minus 1 times 1 is minus 1. Being added to 1 gives me 0. Minus 1 times minus 3 is positive 3, and when added to minus 3 gives me 0. So the entries that we consequently obtain there is 0, 0, 0. Looking at this augmented matrix, you'll now observe that this is in row reduced form. The rows of zeros are at the bottom. The first non-zero entry in each row is indeed 1, so it's a leading entry. And the entries above and below each of the leading ones are 0. So this is a row reduced matrix, and you can now stop the entire procedure. And following stopping the procedure, you can now read off the solution. So how do you read off the solution? This is the crucial bit. Remember that the first column here represents the variable x, because remember, we took the coefficients of x and we wrote it down in the first column. The second column here represents the variable y, because we took the coefficients of y and wrote it down in the second column. So that means this is column for x, this is the column for y, and this is the column for constants. Right, so what does row 1 tell you in terms of the variables and the constants? It tells you that 1 times x plus 0 times y equals 4. So that means x equals 4, and that's what's been written down there. What does row 2 tell you? Unpack it. It tells you that 0 times x plus 1 times y equals to minus 3. So that means y equals minus 3. And that's what's been written down there. And then we have a row of zeros which tells you nothing. So we have unpacked all of the information, and we have consequently solved a system of 3 equations in 2 variables using matrices. And this was a method called reduction. So this is where I'm going to stop, because I know that I've told you a lot. I need you to re-watch these videos and points where you think you were confused, and try to get to the bottom of each of the steps that were done in here. I will be uploading shorter videos going forward which explains the steps in more detail, doing more examples, which will help you overcome any types of problems that you might have encountered in watching this video. All right.